All right, it's been a couple months since I filmed. It's good to be back. Good morning. Today we start by diving into a tank of water. While we are in the water, we are going to visualize a hypothetical cube submerged in the water. Basically, what we are going to do is analyze a hypothetical cube submerged in a fluid. What the cube is made of is irrelevant, and so is the fluid in which the hypothetical cube is submerged.
Sure.
Flippin' physics.
Let's identify the width of each side of the cube as capital L, the depth to the top of each cube as lowercase d, and the density of the fluid as lowercase rho with a subscript of f. In our previous lesson on fluid pressure...
Oh, that was my dream.
Yes, Billy, thank you for that.
You are welcome.
In that lesson, Billy determined that with increased depth in a fluid comes increased pressure caused by the weight of the fluid. We're going to use that fact to determine the net force acting on our hypothetical cube. There are 6 sides to the cube, each with the same area. Let's start by looking at just the left side of the cube. Bobby, which direction does the force from the fluid push on the left side of the cube?
The water pushes inward on the cube, so for the left side of the cube, that force would be to the right, right?
Correct, Bobby. And to the right is a positive direction. Billy, what about the right side of the cube? Which direction is the force from the fluid pushing on the cube's right side?
Again, the water pushes inward on the cube, so the force on the right side of the cube would be to the left, and that is a negative direction, right, Mr. P?
Yes, Billy, correct. Notice we can do the same thing with the other 4 sides. The force on the back side is toward the front and positive. The force on the front side is toward the back and negative. The force on the bottom side is upward and positive, and the force on the top side is downward and negative. That means the total force on the cube, or the net force, equals the force on the left side minus the force on the right side plus the force on the back side minus the force on the front side plus the force on the bottom side minus the force on the top side.
Oh, and the force acting on all 4 vertical sides of the cube are equal in magnitude because all 4 vertical sides have the same area and are at the same depth in the fluid.
That means the force on the left side minus the force on the right side equals 0.
And the force on the back side minus the force on the front side also equals 0.
In other words, the net force acting on the cube is just the force acting on the bottom side minus the force acting on the top side. Pressure increases with depth, right?
Yeah.
That's why the magnitudes of the forces acting on the bottom side and the top side do not add up to 0.
Yeah.
But then the force on each vertical side caused by the water pushing inward on the cube is not uniform, right?
Yeah.
Then how can we say the force on 2 mirrored sides, like force left and force right, are equal in magnitude? Okay, sure. Technically, because pressure increases with depth, the force also increases with depth. Therefore, the force is actually not uniform on the vertical sides. It is larger near the bottom of each vertical side than near the top. However, due to symmetry, the forces at the same depth on each mirrored side have the same magnitude and therefore cancel out. Yeah, that makes sense. The mirrored forces may increase with depth, however, at the same depth, they continue to have the same magnitude and will cancel out. Thanks, Bobby.
Yep, well done. And again, because pressure increases with depth, the upward force acting on the bottom side is larger than the downward force acting on the top side. In other words, the net force acting on the cube caused by the pressure from the water acts upward on the cube. And in the first dream Billy had, he dreamed about the equation for pressure. Pressure equals the force perpendicular to the surface divided by the area of the surface. We can solve that to get force perpendicular to the surface equals pressure times area. And because each of these forces are perpendicular to the surface, we can substitute pressure and area into our net force equation. And the area of the bottom and the area of the top are equal, so let's just identify that as the area of a side. Bobby, from Billy's second dream, what is the equation for absolute pressure at a depth in a fluid?
absolute pressure equals pressure naught, where pressure naught is the pressure pushing down on the top surface of the fluid, plus rho, the density of the fluid, times g, the gravitational field of the planet, times h, the depth of the fluid, or the distance from the top of the fluid to the location where you are measuring the absolute pressure.
Correct, Bobby. Now we can substitute the equation for absolute pressure in for the pressure on the top and bottom sides of the cube in our net force equation. We get the quantity pressure naught plus fluid density times gravitational field strength times the depth to the bottom of the cube all times the area of a side, minus the quantity pressure naught plus fluid density times gravitational field strength times the depth to the top of the cube all times the area of a side. We can distribute the area of a side in our equation. Notice we have pressure naught times area of a side minus pressure naught times area of a side. Those cancel one another out.
Everybody brought pressure naught times area of one side to the party.
Everybody did not bring those to the party. They just add up to 0.
Oh, it's not a pressure naught times area party.
Nope.
Dang.
And we can factor out common terms to get that the net force acting on our hypothetical cube equals the density of the fluid times the gravitational field strength times the area of one side times the quantity depth to the bottom of the cube minus depth to the top of the cube. Bo, in terms of the known variables, what are those two depths equal to?
Okay, the depth to the bottom side of the cube is the depth to the top of the cube, lowercase d, plus the length of one side of the cube, capital L. And the depth to the top side of the cube is, as I just said, lowercase d. Substituting that in shows us that the depth to the top of the cube cancels out of the equation, but it's still not a lowercase d party.
No.
True. Now we have net force equals density of the fluid times gravitational field strength times area of one side of the cube times the length of one side of the cube. And the area of a side of the cube times the length of a side of the cube equals the volume of the cube. Now, because the cube is entirely in the fluid, the volume of the cube is the same as the volume of the fluid displaced by the cube. So we can replace the volume of the cube with the volume of the fluid displaced by the cube. We now have the equation: net force acting on the hypothetical cube equals the density of the fluid displaced by the cube times gravitational field strength times the volume of the fluid displaced by the cube. Now, I just want to make sure it is absolutely clear. Class, the density in that equation is the density of what?
The cube.
Air?
Right. That is why I ask. That density is the density of the fluid displaced by the object. It is the density of the fluid the object is surrounded by.
Dang, he just said that too.
Right.
Yeah. And we know from our lesson on density that density equals mass divided by volume. That means we can replace the density of the fluid displaced times the volume of the fluid displaced in this equation with the mass of the fluid displaced by the object, or lowercase m sub f. And we get that the net force caused by the fluid surrounding the object equals the mass of the fluid displaced by the object times the gravitational field strength. And that is called the buoyant force. Billy, now that we have derived the equation for the buoyant force, please summarize what the buoyant force is.
The buoyant force is an upward force acting on an object in a fluid. Its magnitude equals the mass of the fluid displaced by the object times the gravitational field strength. Hold up. Mass times acceleration due to gravity? The magnitude of the buoyant force equals the force of gravity that would act on the fluid displaced by the object?
Correct. The magnitude of the buoyant force equals the force of gravity, or weight, of the fluid displaced by the object. You can think of it this way. The upward buoyant force acting on a hypothetical cube of water is equal in magnitude to the force of gravity acting on the hypothetical cube of water and causes our hypothetical cube of water to have zero acceleration. It will remain at rest.
Yeah, that makes sense. And the buoyant force is the sum of all the forces applied by the fluid surrounding the object.
What about buoyancy? Mr. P keeps saying buoyant force, however, he has yet to say the word buoyancy. The definition of buoyancy is the ability or tendency to float in water or air or some other fluid. And the buoyant force is what causes buoyancy.
Okay. Yeah. Thanks.
I will add that the composition of the object which is submerged in the fluid does not affect the buoyant force. Only mass of the fluid displaced by the object and the gravitational field strength determine the buoyant force.
What does he mean by that?
That the material which makes up the object displaced in the fluid does not directly affect the buoyant force.
Oh, so the density of the object displacing the fluid is irrelevant as far as determining the buoyant force is concerned?
Yep,
I guess that makes sense. Thanks.
you're welcome.
Great. So today we derived the buoyant force equation. Next time we are going to go through some specific examples and do some demonstrations. Thank you very much for learning with me today. I enjoy learning with you.